Good afternoon, everyone, and welcome to the Office of the Chief Scientist Science Seminar Series. For those of you who don't know me, my name is Vanessa Swarbrick, and I'm a Senior Science Advisor with the Office of the Chief Scientist, and I'm your host for this fall seminar series. On behalf of our entire team, welcome to the Science Seminar Series. In the spirit of reconciliation, I respectfully acknowledge that today I am joining from our office located on the traditional lands and gathering place for Treaty 6 and Region 4 of the Métis Nation of Alberta. These lands are home to diverse Indigenous people, including the Cree, Blackfoot, Nakota Sioux, Iroquois, Dene, Ojibwe, Saulteaux, Anishinaabe, Métis, and Inuit peoples, and many others whose histories, languages, and cultures continue to influence our communities today. Wherever you find yourself today, I encourage you to recognize and acknowledge the relationship that the First Nations, Inuit, and Métis have with the land upon which we all live, work, and learn. In the keeping with the tradition of gathering, these science seminars provide an opportunity for us to get together, to exchange knowledge on interesting science happening across Alberta in an open learning and sharing environment. The hope is that through our dialogue today, we are all able to improve our awareness and understanding and to put this knowledge into practice to support evidence-informed decision-making wherever that's occurring. And so with that, today I'd like to welcome Dr. Jen Beverly from the University of Alberta. Jen is an associate professor in wildland fire at the University of Alberta and a former federal government research scientist. She holds an MSc and PhD degree from the Faculty of Forestry at the University of Toronto and a Bachelor's of Environmental Studies from the University of Waterloo. Her fire research investigations have spanned over 20 years and include studies addressing post-fire ecological effects, fire behavior prediction, fuels management, fire and climate interactions, wildfire evacuations, escaped fires, value at risk mapping, and strategic risk assessments at both community and landscape scales. In addition to Jen's academic experience, she's also has experience being a wildland firefighter, where she spent 6 years working as an Ontario fire ranger and a former Helitack crew leader. So with that, I'd like to pass the floor over to Jen and welcome her to the presentation where we're going to learn about some wildfire management in the country.
Thanks very much. And thank you so much for the opportunity to be here today and to delve a little bit deeper than I usually get to do in presentations because we have a full hour. So today we're gonna talk about fire risk, and I was watching as some people were joining, and I could see lots of familiar names there. For some of you, this might be a repeat of some slides you've seen in the past, but I do have some new stuff as well. And for those of you who are new to this topic, I really wanted to give you some basics and some introduction as well as the more advanced stuff that we'll move into. Yeah, I've got some great photos, as there always is with fire, so it should be interesting, engaging 45 minutes or so, and then I'm really looking forward to your questions. So this image up here, I'm sure many of you saw it, if not all of you. Really iconic image of the Donny Creek fire in BC. That's just south of Fort Nelson, and it was taken in June. I think this is probably going to endure as a really iconic image of the 2023 fire season in Canada. And what a season. I mean, really the worst on record by a long shot. Over 18 million hectares were burned across the country, 2.6 million in Alberta alone, an estimated 200,000 evacuees. And actually, I think you could probably up that to closer to 250 once the numbers all get compiled. Extensive structure losses, multiple firefighter fatalities. Fire management agencies across Canada were obviously quickly overwhelmed by the fire activity, and the latest stats I heard from CIFC, the Canadian Interagency Forest Fire Centre, is that there were over 7,000 personnel imported from other countries, 12 different countries. And then when you look at the number of days they worked, it works out to about 720 plus person years of work. So really kind of an enormous and momentous fire season. And I want to come at this from the initial context of Canada and nationally, and I'll explain why. But I'm going to actually be showing you a lot of insights from specific to Alberta as I go. Let's just go back here to the Donny Creek fire. Here's another shot of it. Now this is notable. It's in northeastern BC, but it was notable because of its size, around 600,000 hectares, and that's the largest burned area by a single fire recorded in British Columbia. But let's keep it in context. And so below, I'm showing you the outlines, the actual, this is from GIS, so the actual proximity of the Donnie Creek fire, almost 600,000 hectares, in relation to the Chinchaga fire from 1950 that crossed over into Alberta, 1.4 million hectares in size. So, the fires, and we saw it, like, it doesn't get to make the list as the largest fire in BC, even though Chinchaga started there, because it's divided up. But the Donnie Creek fire isn't really that unusual alone as a fire in this part of the world. And it's not new. We've had big fires in the Boreal in the recent recorded history, and so the fires like this weren't what made the season unique on their own. Here's another captivating image from the fire season, again, one that you've probably seen, and that's courtesy of Alberta Wildfire. But this was the one near Edson, almost 200,000 hectares. Fires like this are part of the natural ecological process in the boreal forest and many other forest ecosystems across the country. These forests were built to burn, and high intensity crown fires that come through burn all of the suspended needles and abundant fuels in the forest canopy. They pop open serotinous cones. So those are cones like lodgepole pine, jack pine, and semi-serotinous cones with black spruce that are covered in a bit of a waxy resin. The fires are necessary to pop open those cones, release the seed, clear off the biomass on the forest floor, set the stage for regen. And over time and across large areas, it's these fires that create the healthy forest mosaic of different ages and stand types. And it's really, a mesmerizing, captivating, in terms of the visuals process, and really a natural wonder. And to see these kinds of fires live in person is really incredible. And it's actually, when I was contemplating why is fire so mesmerizing, even just sitting around a campfire watching this inanimate thing that's seemingly alive. And the other cool thing about it as a chemical reaction, it's quite similar to photosynthesis in reverse. So you've got all this stored up sunshine building for decades in these forests, and it's released in this just a few minutes, really, as it passes through this massive release of heat and light, and what a spectacle it is. But over long periods of time, uh, this process is what's keeping the forest healthy, and we know that. Now, the aftermath may seem bleak, and so this is just a photo of the aftermath of that Donnie Creek fire. And but it's also kind of beautiful. There's this stark beauty to these burned over stands, and that really caught my attention when I was a firefighter. This is a shot of me at the helipad at this fire we were at for several weeks, actually outside the fire protection zone in Ontario, so far north that those are the region where the fires are just left to burn, near a small community shown on the inset map there, Bearskin Lake. And it's a community that you can see had been heavily impacted and surrounded by fire prior to me getting there. In the red fire there, the red polygon is the fire I was on. Not a really big fire. Population of Bearskin Lake, under 500 people at the time. But these were the communities really during the time that I was involved in fire suppression operations that were the ones that are most heavily impacted by fire. So very remote communities, lots of fire. And actually, this community had been evacuated in 1989, 1995, 1998, 1999 as well, before I got there. And actually, the fire that I was on was burned over in 2002, the next year. So, tons and tons of fire. And but the beauty of these natural processes really struck me on that particular fire, and I, as an artist in my youth, tried to capture it there. But wrapped up in that story is at the time, fires were not impacting lots of larger communities in Canada. Early in my career as a research scientist with the Canadian Forest Service, I was asked to try to document how communities were being impacted by fire. Nobody was keeping records of this. There was, no central reporting. It was a lot of different agencies involved in wildfire evacuations, compiling their records separately, and some of them not really being compiled at all. So we launched this study to try to extract that information from media records. And the study ran for several years. And during that time, we documented every fire evacuation we could find between 1980 and 2007. And because fires are a spectacle, they tend to appear in the news. And at the time, these were regular newspapers. We didn't have the role the internet is playing today. So we could go back to the archives and try to extract those in a fairly systematic way. Over that time period, right? So almost 3 decades, there was a total of 547 evacuations that we were able to document, and a grand total of 497 homes destroyed, and just over 200,000 evacuees, which I'm quite confident we exceeded in 2023 alone. So that's over an almost 30-year period. On average, the numbers were not that impressive. Per year, under 8,000 people, Canadians, were being affected. On average, 18 homes lost, and a large chunk of that was due to one fire that I'll talk about in a moment. I was only able to document one civilian fatality over that entire time period. When I started sharing these results at presentations and conferences in the years after the study was completed, and as we had generated some preliminary results, I mean, people were generally not impressed and didn't think that this was a really big issue. I presented it to the Institute for Catastrophic Loss Reduction in Toronto in 2009. Fire really wasn't on the radar of the insurance industry at that point. And, this is just in this 20 years ago that we started this study, right? Like, it's just in the span of my career, how things were quite different. Things did start to shift, and actually the fire that triggered us to do that study was the Okanagan Mountain Park fire in Kelowna in 2003. This was the first fire that had in the modern fire management era that had a massive impact on homes. Over 200 homes were destroyed, about $200 million in damages, and notable for very high winds driving the fire. And it was at this point that there was a real turn in the way fire management agencies and even researchers started to think about and pursue risk assessment. It was, a kind of a reckoning around fire suppression mandates as the only thing or the one thing agencies were focused on, and this idea that, well, you can go in there and be proactive and mitigate. And we saw, because of this fire, the development of a national strategy for wildland fire. I was part of the team working on this in back in 2005. It was published, but we actually started the work right after the Kelowna fire. And this was the shift, to take a more comprehensive approach to fire management and to start thinking about characterizing risk strategically and mitigating that risk proactively. And this is when fire management researchers and fire agencies across North America, really, and even more broadly, started to adopt this very engineering approach to risk. Risk is probability times impact. So, what we need to do, all we got to do to strategically manage risk, we're going to go estimate probabilities, and then we're going to look at what the impacts will be associated with those events. And we've got probability and impact, and we're going to be able to mitigate that. As a researcher, when I looked at that Kelowna fire, part of me was like, well, it's an outlier. And, I don't change the way I think about things based on outliers, but then those outliers just kept happening. So there was Slave Lake in 2011, 7,000 evacuees, almost 500 homes associated with the Flat Top complex fires, 700 million in insured damages. And then, of course, the Horse River fire that impacted Fort McMurray in 2016, 3.6 billion in insured damages. And 2 indirect civilian fatalities. Another example out of BC, that was that Lytton fire, quite notable for the speed and the devastation across an entire community. Really destroyed most of that village, and 2 direct civilian fatalities. And then there's this year, and I'm just going to spin through here a bunch of images that I captured from the media of different and agencies posted in the media from different fires that happen across the country. And I mean, I could have picked another 20 of these or more, but all across the country from coast to coast. The images are quite striking in just how similar they all seem to look, one after another, and from early May right through until September, and in some cases fires burning into October. So really, really remarkable fire season. I've already touched on some of the stats, but quite unprecedented. And each one of these events, actually, even though there were so many of them and you saw lots of them, each one of these events really takes this perfect storm to play out. So you've got to have a place fire can transmit to. So you've got to have fuel that's proximate to an ignition source. And it's got to happen at a time when those fuels are receptive, because they're not always available to burn. They have to be very, very dry when the fuel moisture is quite low. And then you've got to have that ignition. It's either going to be a human or a lightning or ignition from another fire that starts it, and it's got to be in the right place. So aligned with the wind, and that wind has got to push it towards more fuel. So the ignition's got to be positioned right and aligned with the wind that leads the fire to more fuel. And then eventually it's got to get to this vulnerable location. Okay. And so, you know, this perfect storm thing, I think sometimes gets lost when we're thinking about hazard and risk and how we assess it. These are what the risk literature refers to as gray swan events. So we know this can happen, but we can't really assign proper likelihoods at all to these events. We can specify the outcome. It's going to be really bad if that house burns down, but we cannot, with any degree of confidence, assign probabilities to these events, right? So we're dealing with incomplete knowledge, and as I go through my slides, I'll explain more with some examples of why we can't assign probabilities to these events. Now, after these events, what you hear most often is people say, well, that was totally predictable. We could have avoided that. It could have been mitigated. And I'm going to run through a bunch of little decision traps that you can fall into when you're thinking about these types of problems as I go through my presentation. And this is the first one I want to highlight, and it's called the hindsight bias. And so this is this tendency to believe after an event that the outcome was predictable and that it would have been obvious beforehand. And this is really, really common. I personally observed it in the aftermath of Slave Lake and Fort McMurray and talking to people. I mean, really smart people that I respect a lot. But there is this tendency after the event to say, well, yeah, we could have predicted this. And I'm going to push back on that and say, no, we couldn't have. And I'll explain it in some of the slides ahead. But the problem with this bias is that it can lead to a false sense of certainty. And so give you this idea that, oh, well, this isn't going to happen again because we know what to do now. We're going to go mitigate it. And it can give you, really, it can result in poor future decisions. Okay. And I'm going to come back to that. Well, let's just look at what the data says. And so what I've mapped here is for the entire Canadian land base. I've mapped the polygons. The red on the map are large fires that are digitized and documented in terms of their actual extent and area from 1920 to 2020. And below, I'm showing the area burned in Canada statistics that we have available. Now, the early years, I've shown those in gray. Most people will say those aren't terribly reliable because we really don't know how comprehensive they are. Now, the orange years there in the middle, the lighter sort of light orange, those are probably the reliable statistics that have been documented fairly well. During going back to about 1959 or so. And then I'm showing 2023, and actually that's not even the updated graph. This is a graph I made in August when we weren't at 18 million hectares yet. So you can see that on the axis here, I've only got it up to 14. So yeah, it's even a bigger spike than is shown in the graph. And so let's just stop and ponder this for a moment, okay? 2023 absolutely redefined what is possible, what we understand to be possible, okay? And what I think it shows us is that under a changing climate, we can see fire activity amplified in ways that we currently do not understand. And I want to really emphasize that because it's something I'm saying a lot, like I don't think we know what's happening. And I don't have any confidence in what could be coming next year because what we've learned is that we cannot rely on past data to tell us what to expect next year or the year after. All right. These past fires occurred under a different climate and they happened on a landscape that does not exist anymore. Okay. And I don't think we know fully what's going on, but I can tell you that there is no model and no expert that predicted we could have 18 million hectares burn in Canada in a single year. Nowhere close. No, nobody said that. Unless you're aware of a publication or a study that I'm not aware of that did. Okay. And the other thing to keep in mind is that almost every risk assessment that I have ever seen relies to some extent on historical data to parameterize the model. And I'm telling you, the past is not going to help us understand what's coming at us. We can clearly see it, the writing's on the wall. Okay. So in particular, I want to highlight like Halifax. Halifax is kind of near and dear to me. I was born there. But I was watching what was going on there in May with fires just outside of Halifax, and nobody was. If you asked the top experts in the country, do we need to worry about the area outside Halifax? Well, look at the red on the map. There's not a lot of red fires over the last 80 years in that part of the world. So if you think you're understanding risk, looking at what's happened in the region or an area or a community in the past, this is not helping you, right? So yeah, I really want to emphasize that. Now, there have been, of course, efforts to try to understand in a more comprehensive way how fire has behaved at longer temporal timelines. And there's studies like our records, in the previous slide, I'm showing you, not even, just over 100 years of data, and really the first big chunk of it's not very reliable. There's studies fire history studies that try to provide some insight going back further in time to estimate fire activity. And, this is just one of them that caught my attention. The key finding was that fire activity in the North American boreal has actually predominantly decreased, and modern burn rates are broadly within historical ranges of variability. But look at the 2000s on these graphs from this study. It's showing there was a heck of a lot more fire in the past. So if what we're seeing now is just consistent with what can happen and we should have known could happen, then maybe we shouldn't have been surprised. So what was causing it all? Well, one of the reasons why I wanted to start nationally at the Canada-wide kind of summary there is because it really was, in my mind, a continental scale kind of issue. When you have the kind of synchrony and fire activity that we saw, the spatial and temporal synchrony across really vast areas that vary by forest type, they vary by management intensity, they vary by fire suppression histories and effort, they vary by land use. Okay. And yet you're getting fire across the country for extended periods of time. All of this tells me that those factors that vary regionally were not driving the process. This was climate that was driving the 2023 fire season. And a couple of things that I would touch on is that omega block that we saw in the spring. Okay, so that's that sort of Greek letter pattern that's resulted in abnormally high temperatures in Alberta, Saskatchewan, Manitoba, and Northwest Territories, and even Nunavut. And those blocking ridges kind of lock weather in place, and they lead to these extended periods of really hot, dry conditions. And that's not unusual. Like the omega block pattern, I learned about that when I was a graduate student over 20 years ago. So we know that can happen. It just happened to play out at a time where we also experienced sea surface temperatures in the North Atlantic that's that lower chart I have on the bottom right, spiking, and it looks a little bit like the area burned graph, like just a completely unprecedented spike in the sea surface temperatures in the North Atlantic. And we know that sea surface temperatures in the North Atlantic are linked to continental scale climate and associated fire processes. And yeah, I did a study on that, showing those linkages in the data and actually in evacuation data as well. linking those large scale climate processes together. So, was 2023 the outcome of just this kind of serendipitous alignment where you had the omega block pattern and then you also had these sea surface temperature anomalies, and it created this very odd thing that is never going to happen again? Maybe. We really don't know. And or maybe it's going to happen every year. I mean, I'm certainly worried about the weather we're having right now, and really unprecedentedly warm November, which I'm sure everyone's enjoying, but it's also really concerning. Like, is this a harbinger of what's coming for next year? We don't know. And I think we have to come to terms with that. We do not know. A couple things I want to point out, kind of tying back into that kind of uncertainty and how we're interpreting this data. So I've highlighted 4 fires here: the Donnie Creek fire and the Chinchaga fire on the left that I already talked about. And then over here on the right, 2 additional fires: the Horse River fire that impacted Fort McMurray, and then this other one, that DA003 from 1980. Okay. Well, let's look at the Horse River fire and then the DA3002 1980. It doesn't have a fancy name. I couldn't find any information on that 1980 fire anywhere other than the polygon that I have documenting its area. But it's about, that's actually a little bit bigger than the Horse River fire in terms of the area burned. But nobody knows about it, or maybe if there's anyone on the call that can inform us about what the impacts of the 1980 fire were. I suspect there were no impacts of note to the 1980 fire. It was just a natural fire doing its thing on the landscape, right? And the reason we're looking at it right now is because I just want to point out that these individual fires are not what's remarkable. And I know there's a lot of narrative around, well, the fires are getting bigger and the fires are more intense, and there's the fires are burning the way they're burning because of fire suppression, and the fires are burning the way they're burning. I want to just let's keep ourselves grounded in what we do know, and that these fires aren't really remarkable. Like the 2016 Horse River fire doesn't really look much different than the 1980 fire. It was different because it happened to impact Fort McMurray, right? And so that's, is that a thing of concern? It is, absolutely, but it's not because we mismanaged fire suppression or fuels or anything else. It's it's the Fort McMurray fire is very consistent with other fires on record. And the thing I want to point out, though, is that for any one of these fires, you're seeing just one iteration of what could have happened, right? So the 2016 Fort McMurray fire could have just as easily have been that 1980 fire that nobody took note of, really. Okay. And there was no way to predict it was going to be the 2016 Fort McMurray fire versus the 1980 fire. Okay. So those are all of those fires are one iteration of what could have happened. So the day Fort McMurray burned, the Horse River fire, well, this is just one snapshot here from the Fire Weather Index System maps posted on Natural Resources Canada website every day. So this is the fine fuel moisture code, receptivity to human-caused ignitions on that day. Really, you could have just taken a dart and thrown it anywhere in Western Canada, and you would have gotten really extreme potential for a fire like that. The entire western part of the country really was receptive to ignition. So where can we expect fires? If we can't predict where the ignitions are going to happen, and I'm going to say I don't think we can do that with any, from a strategic scale, I don't think we can predict where fires are going to happen 2 months before they happen, or even 2 days before they happen. To do that, you've got to be able to predict where lightning is going to strike. You've got to be able to predict where a human ignition source is going to hit the ground. I don't think we can predict where these events are going to happen, but there's things that we do know well in advance. There's these fixed things that we do know a lot about. We know what burns, we know where it is, we know operational capabilities, we know the location of the values. Okay, we can't predict in a strategic way, we cannot predict fuel moisture, what that's going to be on July 15th, 2024. We don't know where the ignitions are going to fall next summer, and we don't know whether they're going to happen on days when they're receptive. So one thing we can do if we're trying to manage risk is to really focus on what we know, those fixed factors that you can know well in advance, and that's the fuel. Now, the problem is, though, that a lot of the way we were looking at fires and studying fires was in a very integrated way. And a lot of the models that were available to us to start to do that as researchers were developed for another purpose. They were developed to inform fire response and suppression, right? And so mitigation, it needs other types of information. When you're looking at fire response, you're looking at things like, well, where are the fires going to start today? Where are they going, once they do start, where are they going to be in an hour? You're looking at ease of ignition, rate of spread, intensity, depth of burn. And that's what, the danger rating system was developed to meet those needs. But mitigation, I'm concerned over much longer time horizons. I want to know the potential impacts and susceptibility and risk assessment. I need hazard maps to inform things like fuel management and containment line planning. So really a different purpose. But what we saw happen was there is researchers and decision makers have continued to rely heavily on the research and models developed for response to inform strategic planning. And that's this status quo trap where decision makers display a strong bias towards alternatives that perpetuate the status quo. Okay. And so when it came time to asking questions like, well, we want to strategically know where we can expect fires to burn so that we can do the mitigation that this new risk framework is requiring, that we turn to that sort of likelihood and impact, and we're going to identify the likelihoods, and then we're going to mitigate it. So when researchers and then agencies that followed started asking these questions, they said, well, we'll just simulate fires using the models that we have. And they use simulation models, Monte Carlo simulations, and so, well, we'll just take the models that we have to grow fires because they were developed for response. And so they needed to grow fires to tell the fire management agencies where the fire is going to be in an hour, fire behavior prediction system. We're trying to solve a different problem, but they just went back to the status quo trap. Let's use the same models that we've always used. We'll do another iteration. We'll grow more fires. We'll look at how often locations burn using that fire event approach to the problem. We'll just look at individual fires. We'll grow them using the models that we have. And then we're going to calculate burn probabilities, and that's going to give us the likelihood we need for the risk equation. And it's just the number of times the location burned, given the chances it had to burn. So in this little example, there's 2 iterations. This spot burned once out of 2, so the burn probability is 0.5. Now, the models that were developed, of course, were doing lots and lots more simulations. But the key point I want to make is that the whole approach to trying to understand the strategic level problem is relying upon old models that were developed for a different purpose, and it's embedded in the fire event and growing the fire event, which requires you to look at not just what you know, the fuels, but it requires you to guess at ignitions and weather as well, and to wrap those all together. Okay. And I use that approach. And so as a researcher with the Canadian Forest Service, I was encouraged to use that model that the CFS developed, Burn P3, and make these risk maps and give them to agencies and tell them to use it to make decisions. And so we grew, in this map, to make this map, we grew 125,000 of those fires and 25,000 iterations, and you make a map showing which places burn more often. And you think, well, the red places on the map, those must be where you focus your strategic mitigation. But remember, we made the map by wrapping up the variable and the fixed aspects of fire together by growing individual fire events. Okay, that's the perspective, the lens through which risk was being assessed. And then Slave Lake happened, a few years after we published this paper. And of course, I looked back at my map and I thought, was this map telling us anything useful about where you might focus mitigation efforts in order to, avert something like what happened in Slave Lake? And I thought, there's really nothing about the map that would have thought, let's go focus on the Slave Lake area. I was quite frankly way more concerned about Swan Hills. So this caused me in the years to follow to think about this. But part of the problem is what I'll call the framing trap. And that's the way you frame the problem is going to profoundly influence the choices you end up making. And part of the problem is that blue and red and yellow is really misrepresenting the information that I have. The map should look like this because the burn probabilities that I estimated with those 125,000 simulated fires are actually pretty low everywhere. And they're really not useful for telling me where to focus my effort on anything, right? Because 99.2% of the time, the areas, didn't burn at the high end of the burn probabilities, and 99.6% of the time there was no burn. And that's not really enough of a range in my mind to heavily influence what you're doing. I certainly wouldn't use it to inform a fuel management or any other decision that's happening in a very focused, localized area. But there's this other problem, the confirming evidence trap. And so we have this natural tendency to seek out information that supports our existing instinct or point of view, and we avoid information that contradicts it. And so all of the modelers that were using this approach sought out information to confirm that it's a good approach. And they really put blinders on when it came to any information that worked against it. I started looking at my maps and noticed that, most of the area burned that happened in the years after I made the map was not happening in the red parts of the map. Actually, it was happening in the lower end of the burn probability range. And that led myself and Neil McLaughlin, who was at that time with the Alberta Wildfire Management Branch, to actually delve into a bunch of different study areas, my study area, as well as 4 areas Neil had modeled, to try to understand if the model was reliable anywhere. This approach of studying risk through the fire event by studying individual fires, simulations of them in this case. And so Neil's study areas, he had been modeling to inform the fire management planning process in Alberta. We took his 4 areas and my one study, compiled it together, published the results, and it was really consistent results across all the study areas. Most of the fire was burning in locations mapped with low to moderate burn probabilities. So the yellow and blue areas of the map are burning. And here's an example of that same approach used to map burn probabilities in Fort McMurray. And this map was made right before the fire that burned through that entire area. Okay, so the things that we tried to share this information and got a lot of backlash from modelers who like using the simulation approach. And I think I can understand it in terms of the sunk cost trap. So we're biased towards making choices that justify past choices. And so modelers who are using those methods are going to continue to invest in and basically justifying the way they've been doing things. And so they're going to continue to say, well, no, we want to continue doing it this way. And then there's also this group think trap. So decision makers accept proposals without scrutiny, suppress opposing thoughts, or limit analysis and disagreement. And so, we provided this analysis and disagreement and saw a lot of people try to shoot it down and say, no, we're going to continue doing burn probabilities. And I said, you can't predict the probabilities of this, but it's still a popular approach that lots of people are still pushing and refusing to accept that there's an opposing evidence and thoughts. But it doesn't matter. We were inspired by what we found. So myself and Neil, and as well Liz Chapman. I think Liz may be on the call. I think I saw your name, Liz. We started to talk about these issues and decide we would try to do things differently, and we would disentangle all those pieces that are modeled together when you look at an individual fire event, and we will take them apart and look at them separately, and we will start with the fuels because we have certainty about the fuels and we know where they are. We went back to some stuff I had done years ago for community assessments of exposure, which is just looking at fuel proximity and saying, hey, if I'm a structure and I'm nearby, hazardous fuels that can drop embers on me or expose me to radiant heat, then I'm in trouble. I'm exposed. And when I had looked at the results of those types of assessments for Slave Lake, because we had done a pre-fire exposure assessment in Slave Lake, What we found is that, that approach did not a bad job at helping us to understand where the fire entered the community. And so Liz and Neil and myself and some others, obviously many that we had discussions with at Alberta Wildfire, led us to go down a different path where we would just develop a very simple metric of that exposure, but run it at the landscape scale. And so we just take a fuel map and, for every pixel there's 80 in this 500-meter window. We look at the hazard fuel and we compute how much of it there is. So in this case, there's 75 pixels with hazardous fuel types out of a maximum of 80. So it's got 94% exposure. Super simple. All you need is one input. It's based on what we know, the fuels. And we made a map for Alberta and we subjected it to the same test as the burn probability stuff. And what we found is that, well, most of the fires burning in that really extreme exposure area. So you saw that skew. These shaded bars are showing you where the fire area burned occurred, and there's a surplus of it. There's more of it happening in areas where there's relatively less of that potential. So there's a deficit of fire in the low exposure areas. And so it's just a real simple way to do this. And I've run it for the whole country. We found the exact same results when we ran it across Canada as a whole. I need to get this published soon, but I've been sharing the results early. And you can see, big fires conforming with the dark red areas of the map, which is not what we saw when we used the probabilistic approach. But there's this complexity trap, and I think this might be my last trap, but modelers should simulate processes at the most fundamental level that's reasonable while avoiding the temptation to add unnecessary detail just because it's feasible. But when you show people a map like this, and I say I'm able to make this map with just one input, they're really not impressed. It's not complicated enough, and everybody wants to make it more complicated. Now you can take the exposure assessments and merge it with weather information that you know the day before, or you have prediction for tomorrow. And you can even merge it with other inputs like ignition, lightning strike data. And you can put those together. In this case, I'm saying, well, let's take that fine fuel moisture code. Let's merge it with the exposure assessment that I have for the whole year. And I know that, today, or for the predicted fine fuel moisture code or observed one, I can see the areas that are both receptive and exposed. And it's reliable, right? It's reliable because the weather predictions are not bad for the day of or day before, and the exposure assessments are pretty good for a full season. And we've added some sort of overlays to that. So we've taken the exposure assessments and used those to also look at the configuration or pathways of exposure. So in this, we take an exposure map around something we care about. It could be community, it could be a habitat that we care about, it could be valued timber stands or anything of concern. And we could say, well, could fire come in from the north? Could it come in from the west? And you can see in this grayscale, high exposure areas are pretty well aligned around the west pathway, but not so much in the north. And so we can do those assessments for communities, and we published that work I guess we published it this year, actually, early this year. This is an example for Rainbow Lake, showing you've got one road in really predominantly from the east, and you've got really no other way to evacuate that community, and a lot of directional vulnerability, potentially fire coming in from that direction, as well as other areas around the community. We've compiled those for all of Alberta to show which regions of the province have directional vulnerabilities based on those exposure assessments. And actually just this month, we've combined it with evacuation planning to show vulnerabilities for evacuations. Obviously, Rainbow Lake is quite vulnerable from having that one road. Other communities, it's more complex, like Whitecourt. Okay, so I'll just wrap up really quickly here. I think I'm just at the 2:15 mark. So I've covered a lot of ground. The takeaways: we're in an era of unprecedented uncertainty and rapid change. We do not know what's happening. That probability times impact framework, it's really not appropriate when we can't assign the probabilities with any degree of certainty. Historical data and antiquated methods, cannot be relied on to plan for the future. We have to focus on what's possible. And that means taking a scenario and contingency planning approach and really abandoning the whole notion that a probability is meaningful. We need to move away from the fire event as that unit of analysis and decouple those variable and fixed risk factors so we can focus on what we know. And we need to be on the lookout for those decision traps that I tried to highlight for you today, because they really plague approaches to risk assessment. And just to sum it up, I talked about the hindsight bias, the status quo trap, the framing trap, the confirming evidence trap, the sunk cost trap, the group think trap, and the complexity trap. And I've encountered all of these in my work assessing wildfire risk. The other thing I encourage everybody to do is welcome opposing views and embrace fast, frugal, simple, agile approaches to risk assessment, because I really believe that we are running out of time. And if it's a complicated model, we don't have time for it. Finally, I want to highlight some key supporters and contributors. Funding from Alberta Wildfire, the Forest Resource Improvement Association of Alberta, the Institute for Catastrophic Loss Reduction, the National Research Council, and really many key people with the Alberta government who have contributed to this work, as well as some students in my lab, Air Forbes, and my postdoc, Nima. And as at Alberta Wildfire, it'd be Dave Schroeder, Neil McLaughlin, Liz Chapman, and Laura Stewart.
Oh my goodness, Jen, that was an awesome talk. And before we sign off, I just want to say thanks everyone for joining. Our next seminar is on the 12th. We're going to be hosting a panel discussion on advancing Indigenous lake monitoring and stewardship in Alberta. We have 4 different speakers lined up for that panel. So I hope you can join us for that. As a reminder, if you're not on the mailing list for these seminars and you'd like to be added to it, or if you have work that you want to share with our team or with the rest of this community through these seminars, please contact us at the aep.ocs@gov.ab.ca email. And with that, the biggest thanks I have today is for Jen and her really exciting, stimulating presentation today. And for the rest of you, thank you so much for tuning in.